Hello guys, welcome to the lesson on inverse and composite functions. Let's begin this lesson with the do now. Just like we've done in class, we're going to do the exact same procedures. So our do now, we have to graph this relation. Now remember, a relation is actually an ordered pair. We defined a relation earlier in the semester as an input and an output value. So here we go, x are our input values and y are our output values. So to graph this, I'm going to begin by doing my Cartesian plane. This is my x-axis and this would be my y-axis. From there I'm going to label it 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5. This is a -5. And 1, 2, 3, 4, 5. That's a -5, -6. So we have 0. Let me get another color. We have x is going to be 0. When x is 0, y is going to be 6. So that's our first dot. When x is 1, y is going to be 4. Here's 4. When x is, there it is. It's kind of getting erased. I don't know why. All right. When x is 2, y is also 2. There it is. When x is 3, y is going to be 0. There it is. And when x is 4, y is going to be 2. This is actually a typo because it should be -2. So I apologize for that. If we were to connect those dots, we find out then, well, that is a very bad line. All right, let's try that again. If we were to connect those dots, we find out that we actually have a linear function. It is actually a line. And if my graphs were awesome and straight, they would probably look more like a line. So I expect you guys to be using straight edges, rulers, or the side of your ID also works. But this is exactly how we would graph it. This would be the graph of our relation. Now we're going to be using this example further into the lesson, so just kind of keep this in mind. So moving on to the next slide, here we have our inverse functions. Our objective is given an understanding of functions, students will identify and write inverse functions. So understanding what a function is, you guys will be able to analyze or to identify what an inverse function looks like and then be able to write inverse functions. So writing this in your own words, we have students will determine if a blank has a blank and be able to blank its inverse. So by filling this in, just like we did in class, we have students will determine if a function has an inverse and be able to write its inverse function. So we're going to identify and write. Here's my identify and write. And that's what we're going to be doing today. So I have about about 11 minutes, or I'm going to run through this lecture really quick. Again, you guys can pause at any point and rewind and look at the examples at your own pace. So I'm going to go through this fairly quickly. Using that mentality, there we go. We kind of jumped into one slide. Here we have our original ordered pair, and we have our original ordered pair. Now I want you guys to use this original data to predict an inverse. What is it exactly? How can we obtain an inverse if we have our original ordered pair, our original relation? Now, the first thing that pops into your mind as an inverse is opposite. But we don't want to change the signs of all of these values, because then that would just be distributing a negative value or a -1. We actually want to do the inverse of this. Now, what this means, if I were to guess, is I would take each one of these values, and instead of having 0 as x, my y is going to become 0, which means my x is 6. So I'm switching these values. So this one becomes 4, 1, 2, 2, 0, 3, -2, and 4. Again, this being a -2, typo, sorry guys. We actually switch all of these. So what I can conclude is that we remember that our x values are all of our inputs, also our domain, and our y values, our outputs, are our range. So what I'm doing is I'm actually switching my domain and my range, or to kind of get it in English terms, I guess you say, we are switching my x and y values. That is all that we are doing. We literally, to find an inverse of our relation, switch the x and the y values. So let's keep this in mind for the next example. Here here they ask us to find the inverse of y is equal to 3x minus 5. Now to find the inverse, just knowing what we've seen so far, I'm literally going to switch the x and the y values. So if I rewrite my example, the first thing I want to do is switch my y and my x. So instead of y is equal to 3x minus 5, I'm going to have x is equal to 3y minus 5. Now that I have that written down, I want to be able to solve for my equation. So in order for me to solve for my equation, I want to isolate y. I want to find out what y is equal to. So in order for me to do this, I have to do PEMDAS backwards, or I have to solve for my function, or for my y value. To solve, I want to cancel out this -5. I get plus 5 on both sides. What you do to one side, you always do to the other. This goes away. I'm left with x plus 5 is equal to 3y. Now to isolate these two, I'm going to go ahead and divide by 3. Divide by 3, what you do to one side, you do to the other. 3 divided by 3 is going to give me 1, or 1y is equal to x plus 5 over 3. This becomes then my inverse function. If I were to compare it up here, so let me take another pill. If I would compare it with this function, or I'm sorry, with this equation, I have that my inverse equation would be y is equal to x plus 5 over 3. This is my original, this is my inverse. Now we have 3 steps. To write every single inverse function can be written if you follow these 4 steps. These 4 steps correlate very closely to what we saw in the previous example. 2 of the things we did in the previous example was switch y and x and then solve for y. So we're going to be doing those exact same things. Now in order for us to follow these steps, the first step we see is get rid of f of x. Well, in the previous example, we didn't have an f of x. So if I were to give you guys an example, f of x is equal to x plus 3. Now the first step we want to do, or step 1, is to get rid of f of x. So how do we get rid of f of x? Well, we know that f of x is actually equal to y. We've studied this before. So this becomes y is equal to x plus 3. Step 2 says to switch x and y. So we're going to switch these values. We end up with x is equal to y plus 3. Step 3 says solve. So now I want to solve. If I solve, I want to isolate y. So in order for me to do this, I subtract 3 to both sides. This goes away. I get y is equal to x minus 3. And my final step is to change back to this notation is called f inverse of x. So my f inverse, if we started with f, we've got to end in f. My f inverse, there's the inverse sign, of x is just equal to x minus 3. So this becomes my inverse. We can use these 4 steps every single time to write any kind of inverse function. And here we have a few examples. So depending on your comfort level, you can go ahead and solve these. We're going to solve these as a class during our lecture. Now we're going to have a bit of vocabulary. We studied composition functions before, and we're going to kind of review these and say, all right, the composition of a function g with a function f is actually we create a new function, and that new function it becomes g of f of x. I created a roadmap that we talked about or we've discussed in the previous sections where we start from the center, we start from x, and then we're going to evaluate at f, and then from there evaluate at g. So if I start from x, I'm going to go ahead and substitute that in. I get f of x. Whatever my answer for f of x is, it can be a number, an equation. I'm going to use that and I'm going to substitute it for g, or my function g of x. And whatever I get there, I get g of f of x. And that is my answer. So we're going to use this roadmap to be able to solve a few examples. So example number 3, we're going to use this exact roadmap. Here we've defined what f of x is equal to, and we've defined what g of x is equal to. So the first one we got to notice is, all right, we're starting from the center. So here's my 2. We're going to evaluate at g and then evaluate at f. So I'm going to draw my map. I evaluate at g. Whatever I get there, I'm going to use to evaluate at f. And whatever I get there is my answer. So we're starting from 2, which means I'm going to evaluate g of 2. Well, then g is up here. So anytime I have an x, I'm gonna substitute that x for the value of 2. So I really have 2 squared plus 2. If I further evaluate, I get 4 plus 2, or 6. So g of 2 is equal to 6. That becomes my answer. So then I'm going to use this 6 and I'm going to substitute it into my function. My next function is f of 6. Here I have f of 6. Again, anytime I see an x for this function, I'm going to substitute with the value of 6. So I get 6 plus 1, or f of 6 is just equal to 7. There's my answer, which means that my answer is 7. Now to properly write the solution, I can't just write 7, because what's 7? 7 doesn't mean anything to me unless it's got something attached to it. So we're saying that the function of g of 2 is equal to 7. And that's how we would write our final answer. You can do the same steps for B and C, and we'll see this in class in more detail. And we have about 4 more minutes before I finish this, this part of the lecture. So let's go ahead and skip to the next one. Now for the next example, we can also evaluate these functions, these composition functions, without actually any real values. If we would look at this roadmap again, here we have that we start with x, we evaluate at g, and then evaluate at f. So if I were to draw it out, I begin with something, I'm going to evaluate at g. Whatever I get there, I evaluate at f, and that becomes my answer. So let's go ahead and start from here. We notice then the most inner value is x, so we have x. We're going to substitute that, we get g of x. Well, g of x is just given to us already. It is our definition up here. We have that is equal to x plus 5 over 3. Cool. So we're going to write that as x plus 5 over 3. Now whatever we get here, we're going to substitute back into our function, which is going to be x plus 5 over 3. And we're going to evaluate x. So anytime we see an x up here, we're going to substitute that x for this entire quantity. So we have that the f of x plus 5 divided by 3. Anywhere I see an x, so I'm going to have that's equal to at 3 times x plus 5 over 3 minus 5. I'm going to go ahead and start evaluating. I can write this as a fraction, and if I have a 3 in the numerator and a 3 in the denominator, they cross out. Well, that just gives us then x plus 5 minus 5, or that just gives us x. So if that's our solution, then we can properly write the solution as f of g of x is just equal to x. Now this other one, we're going to see it also worked out in your class. And if we actually follow our steps exactly like we did before, we come to realize that g of f of x is just equal to x. So what can we conclude between these two? Is that both of these solutions will give us an x. Why would they give us an x? We saw in the previous one that order does matter if you're evaluating from f of g of x or g of f of x. So something we can conclude is, or something that we notice between both of them, is that they're exactly the same, or they give you the exact solution. Well, this is because, and only because, these two functions are inverse functions. So the property for inverse function is stated down here. If f and f inverse are inverse functions, then no matter which way we evaluate these compositions, we will always end up with x. So it doesn't matter which order we pick. If we pick f of g of x, we will get x, or g of f of x, we will get x. And that's only when these two properties are inverses of each other. And here we're going to evaluate, or actually we're going to define the inverse function now that we've gathered all our pieces together. And the inverse function can be read up here. Please make sure to pause your screen at any given moment so that you guys can properly write down any of these definitions or